Entropy is a measure of randomness or disorder of a system. And we can write entropy using the statistical mechanics definition as the Boltzmann constant multiplied by the natural log of the number of microstates that the system can occupy. So for example, if a solid, being ice, changes phase into a liquid, being water, then the molecules are going to fly around at random velocities. And if you take a snapshot of this system at the micro scale, at different times, you'll see that the molecules can occupy more positions and thereby can occupy more microstates. But at the macroscopic scale, you'll see that the water pretty much looks the same, because you're taking the average behavior of a large system of these molecules. And when a liquid changes phase into a gas, the intermolecular forces become less significant, and therefore the particles can occupy more positions and more microstates than water. And we can thereby see that the entropy or disorder of the system increases from the solid phase to the liquid phase to the gas phase of a system. Consider the following state for a gas, which initially occupies volume 1. So it has an entropy S1. And if we remove the stopcock, the gas occupies both volumes. So we'd have molecules entering volume 2. And these are all flying off at some random velocities. And we assume that this volume increase occurred at a constant temperature. So for example, you may be inputting heat into the system to keep the temperature constant. So when the gas occupies a larger volume, the particles will have more microstates, and therefore the entropy increases. So the entropy of state 1 is less than that of state 2. So therefore the entropy increases with an increase in volume. And suppose the gas occupies volume 1 and the temperature is increased, then the molecules are going to fly around faster, and therefore the disorder of the system is also going to increase. Suppose we have a reaction involving gas phase reactants or products. So in this case, ammonia and oxygen are in a gaseous state, and react to produce nitrogen gas and water vapor. So we have the entropy of the reactants and the entropy of the products. And because we have less moles of the reactants, being 7, compared to 8 moles of product, then the product will occupy more microstates, and therefore the disorder or entropy of the products is higher than that of the reactants. Suppose we have the following distributions of gas particle velocities with an increasing temperature. And recall that the temperature is proportional to the average kinetic energy of the system, and the kinetic energy of a gas particle was 1/2 by the mass by the speed squared. So temperature 3 has a larger distribution of gas particle velocities, and thereby has a broader distribution of kinetic energy of the gas particles with an increase in temperature. And consequently, as the temperature increases, the disorder or randomness or entropy of the system increases.